Hi, my name is Vivek Shriram, and this summer I interned with Professor Avi Mayan's lab as a part of the NIH-sponsored BD2K training program in biomedical big data science. Today, I'll be talking about my efforts to predict diabetes risk from lab tests and vital signs with the use of machine learning. Diabetes is a heavily prevalent disease that influences almost 10% of the United States. A variety of symptoms accompany the condition, including increased thirst, frequent urination, extreme hunger, sudden weight loss, fatigue, and frequent infections. The current standard for diagnosing diabetes involves measuring a patient's glucose level, typically through a lab test like the A1C test, which indicates average blood sugar over the past 2 to 3 months. We wanted to see if we could improve this methodology with the use of additional labs and vitals. Our goal is to build a machine learning model that can help develop a biomarker set for the prediction of diabetes risk. Our workflow for construction of the model followed 4 steps. We began with preprocessing of our data to eliminate outlying patients, lab tests, and vital signs. We then paired diabetic patients to controls using demographic data. Afterward, we visualized differences between our case and control sets to identify potentially significant predictors. And finally, we trained a machine learning regressor on our data. A major step in preprocessing involves limiting the number of lab tests and vitals we consider for our model. We filtered out instances that had values more than 2 standard deviations from the mean value for the test, and we also excluded lab tests and vital signs that were missing for more than 90% of the population. After these filtration steps, we decided to limit the lab tests and vital signs we considered even further. With almost 1.5 million total patients in our dataset, we counted up the number of cases for each test and picked the most common 20% in each category. These tables show the 20 most common lab tests and 10 most common vital signs. Our final set of data included 109 labs and 11 vitals. Following the preprocessing of our data, we created our case and control groups and performed matching through the use of the R package MatchIt. Our case set was formed by identifying patients in our dataset with ICD-9 codes corresponding to any form of diabetes. In total, there were 50 different codes that matched this criteria. We then used greedy nearest neighbor matching based on demographic information, including age, gender, and race, to create case control pairs between our diabetic and non-diabetic patients. In total, 46,495 pairs were produced. After generating our case and control sets, we used rolling average plots with a 100-day window to visualize differences in various lab tests and vitals for our diabetic and non-diabetic patients. We can see some discrepancies between cases and controls for glucose measures. We can also see a similar difference for HDL cholesterol levels. For triglycerides, while a difference appears to exist, we can see that it is not as strong as that of glucose or HDL cholesterol. While these specific plots don't give us a clear indication of the effect of race on test results, we can see trends over age and gender. This exploratory analysis helps us to identify predictors that may be influential for identifying diabetes risk. We can also attempt to pick out important variables through the use of effect size calculations. Here, we determined ratios between the values for lab tests and vital signs across cases and their matched controls. We then took the median ratio of each lab test and vital. A high effect size indicates a variable that is high in diabetic patients and low in controls, while a lower effect size indicates a variable low in diabetic patients and high in controls. We can see that these calculations identify several predictors as relevant for diabetes, including glucose concentrations, both regular and whole blood, cholesterol, and weight. We also note some other interesting identifiers, including GFR estimate, a measure of kidney function, and base excess, a measure of the amount of base present in a patient's blood. With the completion of our exploratory analysis, we went ahead and trained our machine learning regressor on our data. I experimented with several different methodologies in R, but ultimately settled on the XGBoost package to perform gradient boosting decision trees binary classification, because it didn't require imputing missing data and it ran quickly. The classifier ended up using 46 out of the provided lab tests and vital signs in its model. We were able to identify labs well known to be associated with diabetes, including glucose and whole blood glucose, hemoglobin, and cholesterol and HDL cholesterol. We also found other less expected markers to be strong predictors, including electrolytes such as potassium and magnesium, and other variables like the total amount of carbon dioxide, the amount of troponin I related to heart attacks, and creatinine related to kidney failure. We can see that these results overlap with our effect size analysis as well. We recreated our classifier with different numbers of predictors to determine how changing the number of variables affects our results. We see that dropping the number of predictors seems to reduce the accuracy of our model. This fact suggests that building classifiers based on a composite biomarker set can serve as an improvement over single biomarker approaches. We also performed accuracy analysis on our classifier to determine how it would react to missing test values. We made a corrupted form of our dataset by creating additional versions of our original data with different proportions of missing values. Looking at the accuracy of our model across different numbers of absent tests, we can see that our accuracy does indeed decrease with more missing information. To determine the overall accuracy of our model, we performed 3 separate rounds of threefold cross-validation. Our resulting average accuracy on our data was 0.7111, with an average area under the curve of 0.789. We see that our threefolds overlap quite consistently, suggesting that our model is robust even with changes to the input data. In conclusion, our classifier accurately identified glucose as a top indicator for diabetes. We also identified several other biomarkers that aided in prediction, including expected lab tests like HDL cholesterol, and more unexpected ones like carbon dioxide levels. Indeed, it appears that factors related to other illnesses like kidney failure or heart attacks, which can commonly occur alongside diabetes, can give us a better way to predict the onset of the disease. Several options exist for future work in this project, including testing different tuning parameters to see if the accuracy of the model can be improved, creating a forecasting version of the classifier that uses just labs and vitals before a patient's first diagnosis with the disease, repeating the classification process for other diseases, designing a web application that implements the model, and training our model on EMRs from other hospitals. Ultimately, we can see that such a biomarker set classifier can be used to aid physicians in patient diagnosis, as well as be used to discover new indicators of disease. I'd like to thank Avi and Zishan for advising me throughout this program, and I'd also like to thank the rest of the lab and the other summer fellows for helping me have a fun educational summer.